Welcome back to this course on nanostructured materials, synthesis, properties, self assembly and applications. Today, we are going to through the module 3 lecture 11, and we are discussing core shell nanostructures, and this is the second lecture of the 3 lecture series on core shell nanostructures. So, module 3 lecture 11 on core shell nanostructures. Now, we already introduced what are core shell nanostructures in the last lecture, and we discussed quite a bit on silica based shells on various types of particles. So, we took examples of silica on metals, on semiconductors, oxides and chalcogenides, and discussed what were the different types of core shell structures that you can make on metals and other things based on silica shell. Now, you can also have shells other than silica like titania. TiO2 is a very interesting material. It is biocompatible, it is non-toxic, it is available in plenty, and hence like silica, titania or titanium dioxide is also a very promising material for various applications such as photoelectrochemical activity, solar energy conversion and photocatalysis. Let us look at one core shell structure where silver nanoparticles form the core and titanium dioxide forms the shell. Here silver forms the core and displays unique activities with applications in both biological and chemical sciences. Now, the titania shell leads to enhanced optical and catalytical properties, especially photocatalysis. This is due to photoexcitation of electron from the titania shell to silver core. So, when light falls on this core shell structure, where you see this is the silver core and the shell is formed of titanium dioxide, then this light generates electrons and holes, and the electrons migrate from the titania shell towards the silver core, and hence the electron and hole are separated, which is a very important aspect of any photocatalytic reaction and even in photovoltaics, where you separate electrons and holes, and this kind of core shell nanostructures are very useful in that regard. Now, how do you make these titanium TiO2 based core shell structures? We discussed little bit on earlier on silica based shell on metal particles, and there we started with an alkoxide of silicon. Here you have to start with an alkoxide of titanium. Titanium isopropoxide is the most commonly used chemical reagent, which is used as the shell forming agent. So, using this people have made silver titania, and under the transmission electron micrograph you can see bunch of dark and light shades, and the dark particle is richer in titanium compared to the region B, and the lighter one is actually where it is richer in titanium, because silver has more electrons. So, scattering by electrons from silver when the electron beam hits will be more from silver rich regions, and the contrast will be more where silver is present. So, if you look at this, the high resolution picture, it is more clear, where you can see inside this is the silver nanoparticle, on top of which there is this core which is made up of titanium dioxide. So, we had yesterday discussed how you can identify what is the core and what is the shell, that is by doing an EDAX analysis of the core and the shell. So, similarly, here if you look at the core, that is you pass the electron beam from the core, you can get a region where there is more predominantly silver. So, here you see silver is there, of course, you also see titanium. However, here you see there is more silver than titanium. So, the silver peaks are enhanced. So, this is coming from the core region, and this EDAX spectrum is from the shell region. So, you have a high density of silver in the core, and which suggests this is a typical core shell structure. And from the lattice fringes which you can see, you can estimate this fringe width and can find out the corresponding lattice planes of silver particles, and this distance corresponds to the 200 reflection plane of silver. And you can also do electron diffraction at this point from these particles and find out the reflections which correspond to silver particle. So, this shows you how to characterize a silver titania core shell structure, where silver is in the core and titania is in the shell. Now, here you had started with titanium isopropoxide as the reagent for the shell, and you can change that reagent. Now, you see this example is based on titanium hydroxyacylate. This is another starting material which you can make using acetic acid in some titanium based starting material, and you get this titanium hydroxyacylate. You have to generate this, and that you can use as the shell forming agent, and you can see this dark region is the core which belongs to silver, and this light region is the shell. And if you change the concentration of the titanium hydroxyacylate, like from 0.67 to 0.25, you are decreasing the amount, and you can see the change in the shell thickness. So, from 0.67 to 0.25 to 0.1, you can change the concentration, and you can vary the thickness of the core with respect to the shell, and you can do the EDAX. Again, you see in this case here you, if you pass the electron beam through the core, because on top of this you will have the titania. So, you will see titanium, and in the core you have silver. So, both titanium and silver can be seen in these EDAX spectra, whereas, if you pass the electron beam from the shell, you can see only spectra due to titanium. You do not see any silver peaks here. Of course, you may have copper because of the grid, and silicon comes from the detector which is used to analyze the X-rays which are coming out due to the electron bombardment of these particles. So, as we discussed earlier, the carbon comes due to some impurities, and the copper is due to the grid, and what silicon comes from the detector, and your material is here, it is silver and titanium coming from the core, and only titanium being seen in the shell, and of course, oxygen is there which can be seen in the core as well as in the shell, because you are passing the beam from the top. So, the shell is on top of the core. So, you will see oxygen also. Now, another property which comes out very much in metal core based species, especially when you have nano sized metal, you come across a phenomenon which is called surface plasmon resonance. Now, this surface plasmon resonance of nanoparticles can be modulated or modified based on some thickness of some other material, and you can modulate the type of SPR band that you get. So, what is a surface plasmon resonance? Now, plasmon, the term especially means quantized oscillations of conducting electrons. Now, it happens because when you have the an optical wave passing through a medium and you have these electron clouds of these nanoparticles, then these oscillating electron cloud interacts, and when there is a resonance between these two, then you get what we call as a surface plasmon resonance. So, it occurs at a particular frequency or a particular wavelength. Now, these plasmon frequency can be related by this equation to the dielectric constant, and to the other things are of course related to some specific constants like the charge of the electron and the mass of the electron, etc. So, when do you get this condition of resonance of the oscillating electrons with the optical wave? That precisely happens when the dielectric constant of your particle, which may be silver or gold or nickel, each one of them will have a different dielectric constant. So, when this becomes the negative of this dielectric constant becomes equal to twice the value of the dielectric constant of the medium through which the optical wave is passing, then you get a condition of resonance, and that is when you see a SPR band. So, surface plasmon resonance is a very important phenomena in metal nanoparticles, and you can modulate this by using a shell around the metal nanoparticle. So, you can see a range of plasmon resonances for the same metal. For example, you have gold. Now, gold, depending on the shape, whether it is a sphere or it is a shell or it is a rod, you will have different region of the plasmon band in the electromagnetic spectrum. So, this is the electromagnetic spectrum, where at this you have the UV somewhere around 300 nanometers or so. So, if you are in 400 nanometers or below, you are in the UV region. Most of the particles that you see them having a surface plasmon band in the visible region. So, this is your visible region, and you see most of them lie in the visible or near infrared region. Of course, sometimes you can stretch it to the mid IR region also by changing the structure, by the shape of the particle. So, for example, gold spheres of particular size can have a surface plasmon resonance band, SPR band, around 600 to 800 nanometers, which lies from the orange to the red region, and that is what you see normally gold particles in the orange red region. Whereas, if you make gold nanorods, you can tune, depending on the aspect ratio of the nanorods, you can tune them from the green to somewhere in the near infrared. So, the surface plasmon absorption, the band can be varied depending on the particle morphology. Here what we are discussing now is what happens to the SPR band or the surface plasmon resonance band of silver nanoparticles when it is covered with TiO2. So, when TiO2 forms a shell on silver nanoparticles, what happens to the surface plasmon band? So, if you see that pure silver nanoparticles of the kind which was prepared in this particular study, it has this type of band, okay, and that band is around 395. Somewhere here you can see that there is a band which can be attributed to the plasmon band at 395 nanometers. Now, these silver particles were obtained by the reverse micellar method or the microemulsion method of synthesis. Now, when you make a shell of titanium dioxide on top of the silver particles, then what happens? This you had this band of pure silver particles. When you put titanium dioxide on top of silver particles, you see you have a very pronounced band, and this absorption is centered around more than 400 nanometers. So, it is around 420 nanometers. So, there is a shift towards the higher wavelength, which is called a red shift, and this shift is around 25 nanometers, and this was synthesized using a particular method where a good coating of the titanium dioxide was present. Okay. Now, if you use some other methods, you can see the shift may be different. So, you can have various types of shifts depending on the type of shell, the type of shell thickness you have. If you have uniform coating of the particle, core particle by the shell, you have a larger shift. So, these three plots show you the absorption bands of silver particle, of titanium dioxide, pure titanium dioxide, and a silver particle coated with titanium dioxide, and that shows a red shift of around 25 nanometers when the shell is formed on top of the silver particle. And you can change this by changing the thickness and homogeneity of the shell on top of the particle. The shift in the wavelength from 395 to higher wavelengths can be modified by changing the thickness and uniformity of the shell. So, this is another detailed plot where you are seeing that different compositions of silver is to titania have been used to, and their surface plasmon bands have been studied. So, you see the peak was broader when the molar ratio was less, and that shows better coating of TiO2 or the better coating of TiO2 was observed only when you use a much larger quantity of TiO2 of 0.67 is to 1, where 1 is silver, and when you use less quantity, the peaks start to broaden. So, the best peak for 1 is to 0.67 is this diamond shaped plot, and which is this plot, and it shows the maximum absorption, and it also shows the sharpest band. All the other bands are much broader. So, the concentration of the shell forming agent is important in finding out the position and the breadth of the band. Now, if you add 2 mercaptoethanol, now mercaptoethanol has an SH groups, and this sulfur of the thiol group will attach itself on top of the silver particle, because silver and gold are they bind to this sulfur, and so whenever you have this mercaptoethanol, this sulfur group will bind onto the silver particle. So, what will that do to the SPR band? So, you will have a damping of the surface plasmon. So, the surface plasmon effect will be diminished when we have any sulphide or any thiol, because silver sulphide will form, and the surface plasmon is due to silver, and when silver sulphide forms or silver sulphur bond forms due to the thiol, then the intensity of the original SPR band of the silver core particle will get diminished. So, that damping effect is because the metallic type of silver layers become demetallized because of the formation of silver sulphide or silver sulphur linkages on the top layers of the silver nanoparticle. Now, coming to another property of core shell structures, This previous one was on surface plasmon. Now, let us look at the photoluminescence, that is when something absorbs energy, then after some relaxation processes it can emit energy, and that emission can take place at a different wavelength. So, that is the photoluminescence, and in photoluminescence you have spontaneous emission of light under optical excitation. The features of the emission spectrum can be used to identify surfaces, interfaces and impurity levels. So, some of the fundamental transitions that occur at or near the band edge of a semiconductor are exciton recombination, band to band transition, that is from conduction band to valence band, and transition from a band to an impurity level, then transition from a donor to an acceptor, and their interband transitions. So, some the PL could be from any of these transitions, right. And so, let us do an example of silver which is coated by TiO2, as we discussed earlier, what happens to its photoluminescence. So, if you look at the silver particle with the titanium dioxide particle and look at their band diagrams. So, the band diagram of titanium dioxide, which is a semiconductor, is shown here. It has the valence band and the conduction band, and for the silver, which is a metal particle, you have the Fermi level here, and the SPR band, this the SPR band is due to this absorption from the Fermi level to this level, and when the electrons are excited in the silver particle, they can be transferred to the conduction band of TiO2, which is lower than the SPR energy level of silver nanoparticle. So, effective electron transfer can occur from silver to TiO2, and then you can have an emission from the this excited state or the conduction band here to the valence band. So, this way you can get the photoluminescence, and this kind of enhancement of the photoluminescence is called, can be due to what is called the SERS activity or surface enhanced Raman scattering activity of the silver metal in core shell nanostructures. So, you can see that if you look at the intensity of the PL, this is the photoluminescence plotted with wavelength. So, you can see the highest intensity is for the silver TiO2 core shell structure. Now, for bare TiO2, bare TiO2 is somewhere here. This is the bare TiO2 and this is the core shell structure. So, this enhancement in the PL can be explained by the surface enhanced Raman scattering activity of the silver metal in core shell nanostructures, and the PL intensity will decrease in presence of mercaptoethanol, like we discussed the effect of silver sulfur linkages. If it is present, it leads to demetallization of the silver particle, and that would lead to a decrease in the surface plasmon band intensity, and also it will lead to lowering of the PL intensity. Now, looking at another example. So, you now let us couple a core and a shell which has the coupling of a semiconductor and a metal. So, we are coupling excitons in semiconductor and plasmons of a metal, and this kind of coupling of two materials which have different types of particles, excitons and plasmons, gives us several opportunities to design new materials for photonic applications. So, the example here is gold and zinc oxide. So, gold has a plasmonic band because it is a metal nanoparticle, and zinc oxide is a semiconductor. So, it will have an exciton, and this is the high resolution transmission electron micrograph of a gold core surrounded by a semiconductor which is zinc oxide. The shell thickness is around 2.4 nanometers, and you can identify, as discussed earlier, using transmission electron microscopy and their electron diffraction. So, if you do the diffraction from the shell region, you will get a pattern which is corresponding to zinc oxide, and when you take a diffraction from the gold from the center, you get a pattern, electron diffraction pattern, or which is called the fast Fourier transform of this image. Then you get a diffraction pattern which corresponds to the gold nanoparticle, and the 111 reflections have been identified. So, now this kind of core shell structure with a metal particle surrounded by a semiconductor which is zinc oxide, what will happen when it is exposed to light? When it is exposed to light, then the shell which is zinc oxide will produce a electron and a hole together, which is called an exciton. So, zinc oxide will have the electron and hole, and then the electron will move to the gold which is at the core. So, the electron gets trapped in the core and the hole remains in the shell. This was exactly what we discussed earlier in the case of silver TiO2, where when you shine light on TiO2, then electron and holes are generated, and the electron is transferred to the metal core which is the silver particle, and the titanium dioxide retains the hole, and so there is charge separation. Exactly similarly, here the metal gold gets the electron from the electron hole pair generated in the semiconductor which is zinc oxide, and the electron gets in the gold particle, and the hole is retained by the zinc oxide. Now, when you do a reaction of this kind of particles with something where you have a donor, a dye like rhodamine 6G. So, this is the dye, and you study the photoluminescence of this dye, then what happens that as there is quenching of the photoluminescence emission from the dye. So, in the absence of any core shell particles, the dye shows a PL intensity which is shown by this. Now, if you increase the content of these core shell particles, then they will trap electrons, because the zinc oxide has got holes, because the electron is now trapped in the gold nanoparticle. So, electrons from the dye which act as donors will be transferred to the zinc oxide which acts as the shell, which acts as the acceptor, and the intensity of the photoluminescence will go down, because the electrons which were supposed to be emitted now are getting transferred onto the zinc oxide shell. So, this can be clearly seen in this photoluminescence intensity, the drop in intensity as we are increasing the concentration of the core shell particle with respect to the dye. So, here the dye is 87 and the particle concentration is 1, and then you decrease 43 is to 1, 29 is to 1. So, the concentration of the dye is decreasing with respect to the core shell particle, right, and then you see a decrease in the photoluminescence intensity. So, this shows how when you have a plasmon, that is a metal particle giving a plasmonic band, and a zinc oxide, a semiconductor which has an excitonic band, when they two come together, what kind of photoluminescence changes can occur. Now, again coupling two semiconductors, earlier we coupled one metal and one semiconductor, now we couple two semiconductors. So, what happens? So, you have two semiconductors, one is cadmium sulphide which has a 2.42 electron volt band gap, and that forms the core, and you have another semiconductor zinc sulphide which has a larger band gap. So, you have a small band gap material which is at the core, and it is covered with a large band gap material which is the shell, and then you try to understand what happens to the photoluminescence. So, the zinc sulphide shell around the cadmium sulphide nano rod. So, the core here is not spherical, but it is rod shaped. It enhances the optical properties by localization of the electron hole pair. So, the zinc sulphide shell suppresses tunneling of charge carriers from cadmium sulphide to surface atoms, and the photo generated electrons and holes are confined inside the cadmium sulphide core. So, the zinc sulphide which is at the shell, it does not allow the charge carriers from the cadmium sulphide, because charge carriers are generated by the in the cadmium sulphide because of this particular band gap 2.42 electron volts, and zinc sulphide is outside the cadmium sulphide. Now, when the charge carriers are created, they are not allowed to go to the surface, but are confined inside, and that leads to high PL efficiency because of this photo generated electrons and holes being present, and that you can see here. So, the dark lines, these dark lines, this is the absorption and this is the photoluminescence. So, you can see the dark one is pure cadmium sulphide with no shell, and it has this kind of intensity. The intensity is here, whereas when you put a shell on top which is zinc sulphide, the dotted line, you see a enhanced signal. So, it has enhanced from this value to it has gone to this value, and for cadmium sulphide covered with zinc sulphide. So, the PL efficiency has been enhanced because you have localized the electron hole pair inside the cadmium sulphide nanorod. Now, let us take an example of a core shell particle which is responding to some change in its environment. So, you have a particle in a say a solution, and there is some change in the solution, say either the pH changes or the temperature changes, or there is an electric field or magnetic field. Then what happens to the core shell particle? Does it change anything? So, if it happens, then we call this a stimuli responsive core shell. The stimuli is the external perturbation which we are giving. So, that perturbation can be in the form of a pressure, a temperature, it can be in the form of a pH or ionic charge, or some kind of influence of the environment, and what happens to the core shell in response to this change in stimuli. So, those kind of core shells which do respond are very useful for some applications, where if you apply a temperature change, you can cause a change in the core shell properties, or you can cause a change in the core shell properties by changing the pH around the system. So, let us look at an example. This is a thermosensitive core shell particle and is being used as a carrier for metallic nanoparticles. So, what do you understand by thermosensitive core shell particles? Thermosensitive means something which is sensitive to temperature, and this is a core shell particle, and it will be used to carry metallic nanoparticles. So, what is this particular example? So, you can see this kind of change. So, this is kind of a polymer, and this polymer is polystyrene NIPA, which is some N isopropyl acrylamide, and you have got silver nanoparticles along with that. Okay. So, you have this kind of composites where you have a core shell. So, this core shell of a specific kind can release silver particles at a certain temperature. So, suppose you change the temperature. So, you can see here the network is very open. When you increase the temperature, it becomes very tight. So, this kind of change in the rigidity of this composite as a function of temperature makes this a thermosensitive core shell particle. And so, what happens here, it is holding the silver particles, here it is going to make the silver particles accessible to something else. Suppose something else wants to react. So, these silver particles will then be able to react. Here it is being held very tightly. So, the silver particles will not be able to react. So, this kind of assembly of core shell particles with polymers, for example, can be used in the presence of water. It swells the thermosensitive network attached, and reagents can diffuse freely to the nanoparticles, and then the silver particles which can act as catalysts will react on them. This is very important for photocatalysis by silver or some other catalysis to kill bacteria, etc. So, we can call this directed catalysis, because only when you want, that is under some condition of temperature, you can release it or you can hold it, and hence these are called thermosensitive core shell particles, and they can be used as carrier systems for metallic nanoparticles. So, this is a TM picture where you see this particle, the core shell particle can be seen, the dark one and the light shell, and you can see the black dots, those are the silver particles. So, you can make them release them like they are here, or you can close them by changing the temperature, and the silver particles then will not be amenable for reaction. So, this is very interesting for many applications where your the core shell particles are thermally sensitive. Similarly, you can have other examples where you can have both pH and temperature sensitive. So, the thermosensitive as well as pH sensitive core shell, it is the same material, but it can act under both pH changes as well as thermal changes. So, this particular example you can see is made up of a tri-block copolymer. So, 3 polymers, one black, one red and blue, you can see, and these have different properties. One of them is pH sensitive, one is temperature sensitive, the other one is, the third one is more hydrophobic in nature. So, a combination of these, if you take and you increase the concentration beyond a certain concentration, which is called the critical micellar concentration, then these chains agglomerate and form this kind of self assembled structures. Now, you can see in the self assembled structures, the black ones are inside, and then the red ones have formed a middle layer, and then the blue ones are on the outside. So, under certain concentration, this tri-block copolymer, each having a particular property, self assemble to form this kind of a structure, and not only it is dependent on temperature, the structure, because here the temperature is some temperature which is lower than what we call the critical solution temperature. Okay. So, when the temperature is lower than the lower critical solution temperature, it is kind of in the dissolved state. We say the critical solution temperature is the temperature when you are in the kind of a dissolved state, and above the critical solution temperature it starts to agglomerating. So, these are terms more commonly used in liquid crystals, etc., but here it is been used for an assembly of tri-block copolymers. And so, you have this kind of structure at a temperature below the CST LCST, okay, the lower critical solution temperature is also called the lower consolute solution temperature. Now, when the temperature becomes larger than the LCST, then you see the structure has become more constricted. These chains which were looking outside have now become constricted. So, there is a change in the structure and the total size of this particle will become smaller. Now, this is one change, that with change in temperature, at lower temperature you have this, at higher temperature you have this. Now, not only that, this can change with pH. So, this particular shape that you are seeing is seen at pH 2, but if you keep the same temperature and you increase the pH to 7 or 6.9, then you see the structure changes slightly. And what has changed from here to there is the red region, the one which changes due to pH, it is pH sensitive. So, the red part, you see there is a slight change in the structure compared to this part. So, keeping the same temperature, if you change pH, the red part which is pH sensitive, this part of the polymer is changing its shape. If you change the pH further to 9.2, it has further opened out, and the overall size of this particle is now much larger than what you started with when the pH was 2. This is all at a temperature, all these three are at temperature larger than LCST. If you do all these pH changes at temperature below LCST, then you will have three different structures like this. So, you have these open chains of the blue block, which is basically a temperature dependent block, but since all of them have the same temperature, this blue part is not showing much changes. They are all similar except the red part, which as we saw at the low temperature case will change with pH. Here also the red part changes with pH. So, you have 6 different type of structures, because you are playing with two parameters, which is pH and temperature, and you have a tri-block copolymer which has dual responsiveness. That means, it gets affected by two parameters, both pH as well as temperature. So, it is a very well designed, a smart drug delivery system. You can put a drug inside and you can vary the pH and temperature, and you can get release of drug at a particular pH, and it is planned or designed in such a way that you want to deliver the drug around pH 6.9, which is close to the pH of the living cells. So, that is what is designed here, and similarly many such combinations of sensitiveness, like here we discuss pH and temperature, two properties to which these block copolymers are sensitive, but you can combine two other properties like something which is responding to magnetism, then you will have a magnetic particle combined with say a pH sensitive particle. So, such combinations of properties will give you advanced and smart materials for the future. This is now another example of a pH labile dendritic core shell architecture for drug delivery. pH labile again means pH sensitive. So, it is sensitive to pH. At one pH it has one structure, at another pH it has another structure, and one of them is a kind of a closed structure, the other is a more open structure which can release the drug. The idea is to deliver the drug at a point of your choice at where the pH is what you know where the drug should go. So, this is planned as a combination of a polyglycerol moiety. So, you have a polyglycerol here which is amine functionalized, and you have this aromatic aldehyde with 3 long chains, alkyl chains. Now, if you combine these two, then you get a structure like this, where these 3 alkyl chains are seen. So, this alkyl chains are on the outer periphery, and the CHO has interacted with the amine group to form an imine bond. So, you get the imine, the carbon nitrogen double bond which links the polyglycerol to this aromatic aldehyde, and you get a core shell structure like this, where the drug can be encapsulated in the core. And what happens at a certain pH, at pH around 5 to 6, which we said is present in the living cells, in the living systems, the imine bond actually breaks. When the imine bond breaks, then the drug which is in the core is released. So, the drug is released at the tumor site where the pH is around 5 to 6. So, this particular example took a drug which is doxorubicin, which is an anti-cancer drug, and it also incorporated a dye, a cyanine dye, so that you can see where the drug is going or where the tumor cell is, and this you can see in this picture. So, the tumor cell you can see here, and you can see in the liver, in the kidney, and when you have the dye with that nano carrier, we call N1 is the nano carrier, and it has the dye, then you can see the tumor cell much more easily. When you have only the free dye, then it is not so clear, it is not very clear, but when the dye is along with the nano carrier, then it is much more easily visible, and you can then even release the drug at the particular point by targeting the nano carrier. Since the dye is going there, the drug will also go there, and you can target the tumor cell. This is in a mice in the laboratory, where you can target the nano carrier along with the dye and the drug, and you can kill the tumor cells specifically. So, this is an application where the pH change has brought about the release of the drug. So, this is a pH sensitive nano carrier which has been designed in combination with 2 molecules, generating a bond which will break in the presence of conditions which are present in the tumor cell. Okay. And then you can, the bond will break and the drug will be released, and the drug will be released at the point where the pH is 5 to 6, and that is in the tumor cell. And so, the tumor cell will be neutralized, and so the normal or the healthy cells will not be affected. So, this is a smart drug delivery system designed for tumor treat or cancer treatment. Now, you can also think of a more material kind of example, not towards biology or not toward medicine, but you can look at properties. For example, can you stabilize some particle by making a shell on top of it. So, the mechanical property or the thermal property of the particle can be enhanced. You can stabilize a particle by forming a shell. So, this is an example of a kind of oxide which has got primarily copper and molybdenum and a small amount of tungsten. So, it has got this kind of stoichiometry, and this is forms the core. This oxide of copper, molybdenum, tungsten forms a core, and the shell is formed by silica. So, this is a core shell particle, and the shell thickness can be varied. So, you can see here it is a thin shell. So, inside you have got this copper, molybdenum, tungsten oxide is inside, and the silica is the shell, and this is a thin shell of around 10 nanometers. Okay. And you can enhance the thickness, and this is around 30 nanometers here, and you can further enhance to 50 nanometers. So, you can vary the shell thickness, that is the thickness of the silica shell on top of this oxide nanoparticle. Now, one property of this particle, the core particle, the copper, molybdenum, tungsten oxide, is that it is normally stable in what is called the gamma type of structure, and when you heat it up, this structure changes to what is called the alpha structure. So, this oxide is stable in two forms, the gamma form and the alpha form, depending on the temperature. Now, the temperature or the transition temperature, because it is undergoing a structural transition. So, it is a phase transition, which we can call it is a first order phase transition, because the structure is changing, right. So, this gamma to alpha, this transition taking place at temperature T1 in the particle which has no shell. So, it is there is no shell around it. Now, if you add a shell on top of the particle, then the gamma particle now has a shell which is of silica. So, you make now a core shell structure. Now, this if you heat at T1, it does not transfer to form alpha. So, what you have done by making the shell is you have made the gamma form more stable. So, it does not change to alpha form at temperature T1. You have to go to much higher temperature, that is T2, which is much greater than T1, and then this gamma form changes to alpha. So, this phase transition will occur at a much higher temperature T2 compared to the particle where there was no shell, and that was a lower temperature T1. So, you can stabilize the particle by forming a shell on top of this. This you can measure. So, this is the same thing, but now in numbers. So, you see the amount of alpha phase. At low temperature, alpha phase is 0, there is no alpha phase, everything is gamma phase. If you increase temperature for the bare particle, this is not core shell, this is only core, and this is core shell. So, this you take it, this is a mistake here, this is core, and this core particle changes into alpha form as you increase temperature. So, as you increase temperature, it is going over to the alpha form and becomes 100% alpha when you are say at around 175 or 165 degrees, okay, 175 degrees. Whereas, if you make a shell on top of the core, then it becomes alpha only after you go to higher temperature. So, there is a shift of nearly 100 degrees. So, there is a shift from this temperature, which was 165 or 170 to something like 240. So, there is a large shift in temperature between these two. This is the pure core structure and this is the core shell structure, and there is an enhancement in the temperature at which the transition from the gamma phase to the alpha phase occurs. And this can be plotted in another way, that if you increase shell thickness, what happens to the transition temperature. So, the transition temperature keeps increasing as you increase the shell thickness. These are plotted from the 90% of this curve. So, this is 100%, this is 90%. If you take this value of the temperature, then you take this curve, and if you take 10%, 10% is here. So, if you take this temperature or this temperature, then you are on this part of the curve. You can take either of them, both of them show that the transition temperature changes as a function of shell thickness. So, what you learn from this is that if you make a shell on top of the core, the stability of the core has been enhanced by the shell, and the core transforms at a much higher temperature than it would if it did not have the shell. So, today we will stop our discussion on core shell nanostructures here. We will continue our discussion on core shell structures in our next lecture of this 3-part series. So, today was the second lecture, and you will have one more lecture on core shell nanostructures and the applications of core shell nanostructures. So, thank you and see you in the next lecture.